this is a lab session. Therefore, all we're going to do now is very, very quickly write what we need, and then I'm going to give you a couple of tips as to what to do next. We're all going to head up to the lab, and we're going to simulate the simple pendulum. The planar, simple pendulum. Right, so the first thing I'm going to do is I'm going to get right into it. You'll notice I'm going very fast. That's because I don't want to waste your lab time. So, next, that's our position vector in space. What I'm going to do, very briefly, is I'm going to change Newton's law from Cartesian coordinates to polar coordinates. And I'll use this result to derive the equations of the simple pendulum. Right, in Cartesian coordinates, remember, F equals MA equals M d squared this vector by dt squared. And we know how to get the second derivative of this vector. Very simply, in Cartesian coordinates, it's just the second derivative of the x and the second derivative of the y components, second separately. Well, in polar coordinates, we have to think about these derivatives. And what I'm going to do is I'm going to look at the derivatives of the polar unit vectors. And you'll see how from that we can use that to derive everything we need. So, dr hat by dt, theta hat by dt, this is d by dt, cos theta sine theta, now d by dt, so I del by del theta del t, so that's theta dot, and we'll discuss all this stuff in more detail tomorrow. Minus sine theta plus theta equals theta dot theta hat. Theta hat by dt, that's d by dt minus sine theta plus theta, which if you work it out, minus theta dot r hat. Right, that's all we need. Why? Because r is xy, our position vector. So we can also think of that as x is r cos theta, y is r sine theta. You'll know what we're doing now, so I'll take it away. R hat. Right. Now we're quickly going to convert this equation into polar coordinates by converting the second derivative into polar coordinates. I'll do that then. Okay. dr dt, our position vector, is d by dt. R hat, product rule, R dot R hat plus, when I say dot I mean the time derivative of the quantity, plus R, the R hat dt, which is theta dot theta hat, theta dot theta hat. Let me take the second derivative then, d squared R dt squared. Yes. This is all going very fast, you'll see it again tomorrow. I just need to derive something for you. Right, so, that's d by dt. This guy. R dot R hat plus R dot theta hat, which is R double dot R hat plus R dot times by that guy, theta dot theta hat, plus R dot theta hat plus R dot R. Line of product rule here, theta hat. This is the kind of feat you'll have to do back in the exam. Plus, R theta dot minus theta dot R hat, which is equal to, let's group, R double dot minus R theta dot squared, R hat plus, just go down like that again. Just put it around with right, so plus, and now we've got two of these and one of these. R theta double dot plus 2R dot theta dot. Right, that's the second derivative. Let's substitute it back in there so we can get the full force. So, this is laws in polar coordinates. M times that thing. R double dot minus R theta dot squared R hat plus R theta double dot plus 2 r dot theta hat. Right, that's it. So what we're going to do is we're going to simply get radial and tangential components of there by dot producting with r hat and theta hat on both sides of these equations. So r hat dot f is equal to, when I dot product this with r hat dot theta hat is 0. Even at this speed. You know that answer. This guy, r hat is 1. So we only keep that. M r double dot minus r theta dot squared theta hat dot f is equal to m similarly r theta double dot plus 2 r dot theta dot. That is Newton's laws in polar coordinates. Notice, just quickly, that they're not looking very similar to Newton's laws in Cartesian coordinates. That's a property of Newton's laws. They are ugly. They don't transform nicely. Later when we do Lagrange's equation, beautiful. It looks exactly the same in both. Right. For us, right now, we don't care. All we care about is deriving the simple pendulum's equation of motion. So let's draw the simple pendulum. What do I mean by simple pendulum? I mean, some guy like this. The length of this rod, this thin, massless rod, is constant. It doesn't change. It's constrained. It's to be equal to alpha. Right? The pendulum is at some angle, theta, which is allowed to change, and it swings. Right. Now, just briefly, I'm going to add coordinates to this picture. But the way I'm going to do it is I'm going to rotate my x and y frame, y. When I take my x and y coordinates generally, x, y, and I want to put in r and theta. Theta is the angle with what axis? The x-axis. In order to keep that going here, where does the x-axis need to point? Down. So the x-axis is going to point down, and the y-axis is going to point across. Right, so that's x, y axis. Now I'm going to put them down on this figure, right? Then I can use polar coordinates in this figure the same as always. Right. Because it's Newton's law, I need to know what the forces are. There are two forces acting on this bar at the bottom here. mg for gravity and T, tension in the rod. Correct? Right. So what are they? mg is acting in which direction? Which is what? X hat. Right. And tension is acting in which direction? Inwards, which is minus r hat. Those are my forces. So, all I now need to do is one final thing. What do I know about the system? The length of the rod does not change. R dot is 0. R is constant. Right. R is equal to L. I can substitute that into equations. Those guys up here. Substitute R dot equals 0. R equals L. Into those equations. Yeah.
I've got a question. The F is supposed to MA. Yeah? Where like the second derivative, look inside the bracket.
Up here.
Yeah. Yeah. When you're deriving there, you didn't have F prime. I mean like F head. I mean R head, which is in front of theta square. R head over there. Yeah, so actually theta head at the end. So I don't know what happened
at the end. All I did was I grouped the terms that had an R hat and I grouped the terms that had a theta hat. So you're welcome to check my derivation here. And right. I'm sorry, I'm not giving a lot of time just because I want to get to that. Right, so very briefly, we've got two forces acting on the system. We want to work out how it moves. We know that the length is constant. R equals L, R dot equals 0. Those laws, what do they become? R hat dot F now becomes R double dot is equal to 0. R is equal to L minus ML theta dot squared. is equal to, there are my forces. I must dot those with r hat as well. What do I get? mg r hat dot x hat minus t. Right. Theta hat dot f is equal to, I've got another there. M, r dot is 0, goes away. R is L, theta, double dot, is equal to, dot this guy with theta hat. What do I get? mg x hat dot theta hat plus naught. Right. The first equation we can use to find the tension. Tension is the force of constraint. We'll talk about these in more detail tomorrow. It's the force that keeps the pendulum moving in the motion we need it, but it won't tell us the equation of motion. The second equation will. So let's look at it carefully. Okay, let's solve it. ML theta double dot is equal to x hat dot theta hat. That's going to be x hat, which is 1, 0, theta hat, which is minus sine theta cos theta, dotted with each other, minus sine theta, equals mg times minus sine theta. Okay, we're just about done. Let's divide through by m, it cancels out. Divide through by L, we get theta double dot equals minus g over L sine theta, or as we more commonly write, theta double dot plus g over L sine theta equals 0. Right. That's the equation of motion of the simple pendulum. What does it tell us? It tells us how theta varies with time. Faster, slower, faster, slower. That motion, fully described by this equation. Second order differential equation, what do you need? Initial position, initial angular velocity. Those are what you're going to put as inputs to your numerical simulations. So now we're going to take this equation, we're going to go to the lab, we're going to simulate results of this equation in MATLAB or Octave. We're going to produce a file. The file is essentially going to contain time and angle. And it's going to say, okay, at time 0 the angle was whatever. At time 0.01 it was the next thing. So on. That's going to be a .dat file. We're then going to put that .dat file, pdata.dat, in the same directory as a Blender file, which I've set up for you. Go to Blender and watch the pendulum swing. Let's go.